In this video, we will talk about matrix operations. This is the summary slide, which we'll go over in the next 5 minutes, and then afterwards we'll take each topic in a little more detail and with more examples. We'll start by talking about sums of two matrices. So when you add two matrices, that's simply summing the corresponding columns of A and B. We'll also talk about multiplying a matrix times a scalar. That is, if you multiply a matrix A by a scalar R, you just multiply all the corresponding columns of A by R. We also have this notation that A sub ij is the entry in the matrix A that is in the ith row and jth column. So here we have the matrix. So A11 is the first row, first column entry. A21 is the second row, first column, whereas A22, second row, second column. Then we will come to this theorem that talks about properties of matrix addition and scalar multiplication. And then we'll look at matrix multiplication. So to multiply a matrix A by a matrix B, that's equivalent to multiplying the matrix A by each of the column vectors of B. And this matrix times vector is something we know how to do from previous videos. But there's also another efficient formula to do the product, which we will go over as well. And then we have properties of matrix multiplication, and just as important, we have three properties that matrix multiplication does not follow. For example, one, matrix multiplication is not commutative. In general, AB does not equal BA. Second, cancellation laws do not hold for matrix multiplication. So if AB equals AC, you just can't cancel the A's on both sides of the equation and conclude B equals C. In other words, that's not a valid thing to do. And also, if AB equals 0, you cannot conclude that either A equals 0 or B equals 0. Last, we'll talk about powers of a matrix. So A to the K is just the product of K copies of A. And then last, we'll talk about the transpose of a matrix. And that's where each row becomes a column. And then we'll look at different properties of the transpose. So that is our overview. So we'll back up and we'll start with sums and scalar multiples of matrices. To add two matrices, they need to be the same size. So we're going to assume A and B are both M by N matrices. Then A plus B is the M by N matrices whose columns are the sums of the corresponding columns of A and B. And then the scalar multiple R times A is the matrix whose columns are R times the corresponding columns in A. For example, if A is equal to 4, 1, 0, 3, 5, 2, and B is equal to 1, 3, 1, 5, and 1, 7, and C is equal to 2, 0, negative 3, 1, then A plus B is the first column of A added to the first column of B. So that's going to be 4 plus 1 and minus 1 plus 3. Then the second column of A added to the second column of B. That will be 0 plus 1 and then 3 plus 5. And then finally the third column of A added to the third column of B. So that will be 5 plus 1, 2 plus 7. And our final answer will be 5, 2, 1, 8, 6, 9. And then finally note that A plus C and also B plus C are undefined because A and C are different sizes. Similarly, B and C are different sizes. Our example of a scalar 2 multiplied by a matrix B, that's each column then of B is going to be multiplied by 2. So we multiply this first column, 1, 3, by 2. So that's 2 times 1 and 2 times 3. The second column multiplied by 2 will be 2 times 1 and 2 times 5. And the last column, 1, 7 by 2, is 2 times 1 and 2 by 7. So we'll get 2, 6, 2, 10, and 2, 14. Then finally, we can have A minus 2B. So I moved the matrix A, or I copied the matrix A over here, and my 2B I copied over here. So subtracting, we're going to subtract the first column minus, that's the 4 minus 1, minus 2, 6. So we'll get 4 minus 2 and minus 1 minus 6. Our second column, 0, 3, minus our 2, 10. So we have 0 minus 2 and 3 minus 10. And then finally, our last column, 5, 2, minus 2 14s. That's 5 minus 2 and 2 minus 14, which will give us 2 minus 7, minus 2 minus 7, and 3 minus 12. I have moved this example over here a little smaller for your reference. The next thing I want to mention is notation. So A sub ij is the entry in the matrix A that is in the ith row and jth column. So in other words, if I wrote out this an m by n matrix, m rows, n columns, then my A11, that's my first row, first column. A12 entry, that's my first row, second column, and I can keep going on. My A13 is my next entry because it's the first row, third column, and I go up to A1n. Here, in my second row, I have A21, that's second row, first column, A22, second row, second column, the next will be A23, A24, all the way up to A2n. And then I keep going, so I'll have A31, A4, in this column I'll have A11, A21, A31, A41, up to AM1. And then going across, I'll have AM1, AM2, AM3, up to AMN. So for example, given my matrix A that we looked at before, that's 4 minus 1, 0, 3, 5, 2. A11 is the entry that's in the first row, first column. That would be 4. A12 is the entry in the first row, second column. So first row, second column would be 0. A13, first row, third column. So this is the first row, third column will be 5. A21, this is second row, first column. So here's our second row, first column will be -1. A22, again, second row, second column will be 3. And A23, that's the second row, third column. So that'll be number 2. Once we've defined how to add two matrices together as well as multiply a matrix times a scalar, we have this theorem that has different properties of matrix addition and scalar multiplication. So we'll let A, B, and C be matrices of the same size, and R and S are going to be scalars. Then A plus B equals B plus A, so there's commutativity in the addition. A plus B plus C is equal to A plus B plus C, so there's associativity in addition. A plus the 0 matrix is A. We have R times A plus B is equal to RA plus RB, so there's this distributive law of the scalar. And then we have R plus S times A is RA plus SA, again sort of a distributive law. And then we have R times SA is equal to RS times A, so we can group the scalars together first. And we'll just do a proof of A plus B equals B plus A. And the others are somewhat similar. Since we defined addition of matrices in terms of columns, that's what we're going to look at the columns. So the jth column of A is AJ. That's the vector. And the jth column of B is BJ. So the jth column of A plus B, according to our matrix addition, is AJ plus BJ. Now these are two vectors, AJ and BJ. And by vector addition, vector addition is commutative, so we can switch the order. So that's BJ plus AJ. But this is simply the jth column of B plus A, and therefore these two are equivalent. So just looking over this, what we do is we take our definition of matrix addition in terms of our columns, and then when we're looking at columns, we're looking at vectors. So we can use our properties of vector addition, and then once we've done that, we switch the orders such that then we can convert back and talk about the definition of matrix addition. Next, we can talk about matrix multiplication. So we're going to assume A is an M by N matrix, and B is an N by P matrix with columns B1, B2, up to BP. Then the product of AB is the M by P matrix whose columns are AB1, AB2, ABP, i.e. A times B is equal to matrix A, and then we've written matrix B in terms of its column vectors, and then we just multiply each column vector by A. I've moved this definition up here for reference so we could do some examples. First is to compute A times B when A is equal to the matrix 2, 1, 3, negative 5, and B is equal to the matrix 4, 1, 3, negative 2, 6, 3. The first thing to notice is A is a 2 by 2 matrix, and B, there's 2 rows, 3 columns, so it's 2 by 3. Remember, it's always rows, columns, and I had to keep saying that to myself, rows, columns, until finally I knew that M by N is M rows and columns. So 2 by 2 and 2 by 3. So I wrote that out, 2 by 2, 2 by 3. And the thing about matrix multiplication is these middle numbers, so the last number of A and the first number of B have to be equal in order for matrix multiplication to be defined, and you'll see why that is the case. And then if you think about these two canceling out, what you're left with, A times B, is going to be a 2 by 3 matrix, so your solution will be 2 by 3. And now we can actually do the matrix multiplication. So according to our rule, we're going to multiply A times each of the vectors because we know how to do matrix vector multiplication. So I put my matrix A here times B1, which is the first column vector, 4, 1. And then I do my normal matrix vector multiplication, which is the dot product 2 times 4 plus 3 times 1, and then 1 times 4 plus negative 5 times 1, and I get 11, negative 1. Similarly, I do A, B2, so here's my matrix A, my second column of B, which is 3, negative 2, and I'll get 0, 13. And then for B, A, B3, I have my matrix A, and then my third column vector of B, which is 6, 3, will give me 21, negative 9. And now I can make my matrix AB. I put in my 11, negative 1, my 0, 13, and my 21, negative 9. So this is my final answer, and you'll notice it's 2 rows, 3 columns. That's the 2 by 3 we had discussed before. A last note, you can view matrix multiplication as each column of AB is a linear combination of the columns of A using weights from the corresponding columns of B. So for example, for each column of AB, so let's consider the first column of AB, which ends up being 11, negative 1. And we got that by multiplying A times B1. Remember, we got that there. So we can view this as a linear combination of the columns of A. So the columns of A are 2, 1, and 3, negative 5. And it's a linear combination using weights from the corresponding column of B. So that means since this is the first column, we're going to use the first column of B as our weights, which is 4 and 1. So here's our scalar 4, here's our scalar 1, and the linear combination then of our columns of matrix A will give us our 11, negative 1. That seems to be a very long-winded explanation, but I think when you just look at the math, it actually is a shorter, easier way of understanding it. We can think of matrix multiplication in terms of mappings and linear transformations. Remember in our previous video, we said that linear transformations were exactly those that could be represented by matrices. So we can think of the matrix as a linear transformation, in which case we can take a vector x, multiply it by a matrix B, and we get the new vector bx. And then we can multiply our new vector bx by a matrix A and get the vector A times bx. Or we can think of this, instead of going in 2 jumps, we can think of this as a composition of 2 linear transformations. So we can think of this as taking x, multiplying by the matrix AB, A times B, and then we can get to the same vector, A times the vector bx. So here we have A times the vector bx is equal to the matrix AB times the vector x. Using this sort of picture then, we could say AB is the M by P matrix whose columns are AB1, AB2 up to ABP, because that's how we defined our matrix multiplication, i.e. AB is equal to A times B1, B2, B up to BP, which is just AB1, AB2, A up to ABP. So if A is M by N and B is N by P, and again these two terms have to agree, and what we're going to end up with is an M by P, and X is an R P, then Bx, when we multiply X times B, we're going to get X1, B1 plus x2, the vector b2, up to xp, the vector bp. This is just the definition of matrix times a vector. Then in turn, if we take A times our bx, the vector bx here, we're going to have A times x1 b1 plus A times x2 b2 up to A times xp bp, because that's how we define matrix multiplication. And it's because it's linear, we can take out the x and we get x times ab1 plus x times ab2 plus xp times abp, because matrix multiplication is linear, and then what we get is this is just equal to a times b. So we have ab times x. Now we'll do a couple of more examples of matrix multiplication. So if A is 3 by 5 and B is 5 by 2, what are the sizes of AB and BA if they are defined? I like to write this out. So A is 3 by 5, B is 5 by 2. So remember, these two have to match, and then you kind of ignore them to get your final answer is 3 by 2. So A times B should be 3 by 2. So if we want to know about B times A, so B is 5 by 2 and A is 3 by 5. Since these two do not match, we can't do the multiplication. So B times A is undefined. And I kind of drew out this generic example to show you why they need to match and B times A is undefined. So if B is 5 by 2, that's 5 rows by 2 columns, so something like this. And A is 3 by 5, that's 3 rows, 5 columns, so these are the components of A. Then when I multiply B times A, that's the matrix B, and then column by column, you multiply by the column. So here, I just wrote out B times A1. So here's B, and here's my A1, and as you can see, normally we take the row times the column, so we'd have B11 times A11 plus B12 times A22, and now we have nothing to match this A31. So that's exactly why it doesn't match, and these two need to match up. So for matrix multiplication to work, the number of elements in this first column, which is actually the number of columns, right? The number of elements matches the number of columns. There's 2 columns, so there are 2 elements in this row. It has to match the number of elements in this column, and the number of elements in each column is equal to the number of rows. That's why here the column has to match the row. Now that we've learned how to do this matrix multiplication in terms of our matrix vector multiplication that we have learned in previous videos, we can use this efficient matrix multiplication method. So if the product of AB is defined, then the entry in the ith row and column J of AB is the sum of the products of corresponding entries from row I of A and column J of B. So if AB sub ij denotes the ith, jth entry in AB, and if A is m by n, and then AB sub ij is equal to AI1 B1j plus AI2 B2j up to AIN BNJ. We will do this example here to illustrate this definition of matrix multiplication. So A is equal to 2, 1, 3, negative 5, and B is equal to 4, 1, 3, negative 2, 6, 3. When we do AB, we are expecting our solution to be a 2 by 3. So I kind of wrote the elements here. So AB of 1, 1, that's the first row, first column. AB of 1, 2, first row, second column. AB 1, 3, first row, third column. AB 2, 1, AB 2, 2, and AB 2, 3. So now if I want to calculate AB 1, 2, that's I is equal to 1 and J is equal to 2, I can use this formula. That's A of I1, which is 1, 1, B of 1, and then J is equal to 2, so B of 1, 2. Plus, here we have A of I2, so that's A of 1, 2, plus B of 2, J, so that's B of 2, 2. So that's going to be, coming down here, A of 1, 1, that's A of first row, first column, that's 2. A of 1, 2, that's B, first row, second column. First row, second column, that's 3. A of 1, 2, that's first row, second column. First row, second column, that will be 3. And then B of 2, 2, second row, second column, that's negative 2. So our answer is 2, 3 plus 3, negative 2, which is 0. So our AB of 1, 2, this entry here, should be equal to. And honestly, doing it this way is like really awkward. So what you normally do is when you're going for the ith row, jth column, you're going to take the ith row times the jth column. So for example, here, if we're looking at I equals 1, j equals 1, we're going to multiply or take the dot product of the first row with the first column. So that's going to be 2 times 4 plus 3 times 1. Now, if we want this term here, that's in the first row, second column, so we're going to multiply the first row here times the second column. That's 2 times 3 plus 3 times negative 2. And for the first row, third column here of AB, we're going to take the first row of A times the second column of B, 2 times 6 plus 3 times 3. For the second row, first column of AB, we'll take the second row of A times first column of B. So that's 1 times 4 plus negative 5 times 1. For the second row, second column of AB, we're going to take the second row of A times second column of B. 1 times 3, negative 5 times 2. And finally, we have the second row, third column of AB. That's the second row of A times third column of B. 1 times 6 and negative 5 times 3. And when I say this row times this column, I'm talking about dot product. And I assume you guys have had vector calc before, but if you haven't, it's no big deal. It's just, this times this plus the second term. And so your final answer is going to be 11, negative 1, 0, 13, and 21, negative 9. An example of a larger matrix, A is equal to 2, negative 1, 6, negative 3, negative 5, 3, negative 8, 0, 0, negative 4, negative 7, 9, and B is equal to 4, 7, 3, 6, negative 6, negative 6, 1, 2. So A times B, we have A times B here. We have, here is the first row times this first column, 2 times 4, minus 5 times 7, 0 times 3. For this entry, it's this first row times the second column, 2 times negative 6, negative 5 times 1, and 0 times 2. Then for here, we're in the second row, first column, so taking the second row times the first column, negative 1 times 4, 3 times 7, and negative 4 times 3. And here we're in the second row, second column, so second row, second column, negative 1 times negative 6, 3 times 1, negative 4 times 2, and you can calculate the rest, and we'll get this final matrix, 27, 5, 53, 15, negative 17, 1, negative 58, and 48. I don't know whose idea was to have such big numbers, but here's the solution. Now we can look at properties of matrix multiplication. First, there's an associative law, so A times BC is equal to AB times C. There are right and left distributive laws, so for the left, it's A times B plus C is equal to AB plus AC. There's a right distributive law. And then for any scalar, R times AB is equal to RA times B, which is equal to A times RB. And then there's an identity matrix for multiplication, which we designate IN. N tells us the size of the matrix, how many columns there are. So IMA is equal to A is equal to IN. I've moved these properties over here for your reference, as well as the definition of matrix multiplication, and we are going to prove number 2 using this definition of multiplication. We are going to prove the second statement here. So we'll start with the left-hand side, which is A times B plus C. And we're going to prove that that is equal to AB plus AC. I have the matrix multiplication definition here for your reference since we will be using it. And the first thing is to note that the ith column of B plus C is equal to the ith column of B plus the ith column of C. And this comes from the definition of matrix addition. Now using this as well as our definition of matrix multiplication, where A times B is equal to A times the column vectors of B, so A times B plus C is just A times the column vectors of B plus C. So I have that written out here. And this again is from the column definition of A times B, which is up here. So now since matrix multiplication is linear, this is equal to AB1 plus AC1. This part here is AB2 plus AC2. Up to here, this is ABP plus ACP. And now here, my A times B1 is a vector, plus my A times C1 is a vector. So I can separate these two out. And I can do the same for my second term. These are two vectors, so I can separate them out. And here, these are two vectors. I can separate them out. So I have this matrix here and this matrix here, AB1, AB2 up to ABP, and AC1, AC2 up to ACP. But this is just equal to AB, and this here is just equal to AC. So I have proven what I wanted to show. And now we should just review the three properties that matrix multiplications do not have. First, matrix multiplication is not commutative. In general, AB does not equal BA. And we have this example where A is equal to 5, 3, 1, negative 2, and B is equal to 2, 4, 0, 3. So A times B, you can multiply this out, and that will give you 14, negative 2, 3, minus 6, whereas B times A is going to give you 10, 29, and 2, negative 2. So this is our example where AB does not equal to BA. And in fact, if A is 2 by 3 and B is 3 by 5, then AB, these two match, and we can do the multiplication. We're expecting a 2 by 5 matrix. So AB is defined and is a 2 by 5, whereas B times A, now my 5 does not match my 2. So B times A is undefined. So not only is AB not equal to BA, BA is not even defined where AB is defined. Two other things you need to watch out for: cancellation laws do not hold for matrix multiplication. So if A times B equals AC, you cannot conclude that B equals C. You just can't cancel out the A's. Second, if A times B equals 0, you cannot conclude that either A equals 0 or B equals 0. And both of these, if I had to do a proof, I would just do a counterexample, exactly how when we proved matrix multiplication was not commutative, we proved it by showing a counterexample. Next, we can talk about the powers of a matrix. So if A is n by n, and k is a positive integer, then A to the k denotes the product of k copies of A. And then last is the transpose of a matrix. Given an m by n matrix, the transpose of A is the n by m matrix whose columns are formed from the corresponding rows of A. So we have the following example for transpose. If A is equal to AC, BD, and B is equal to negative 5, 1, 0, 2, negative 3, 4, and C is equal to 1, negative 3, 1, 5, 1, negative 2, and 1, 7. So the definition says to make A transform, we're going to form the columns from the corresponding rows of A. So the first row is AB, so now that's going to be my first column. The second row is CD, so that will be my new second column. B transpose, my first row is 5, 2, so that'll be my first column. My first row is 1, negative 3, that'll be my second column. And my third row is 0, 4, which is my third column. Similarly for C transpose, my first row is 1, 1, 1, so that's my first column. My second row is negative 3, 5, negative 2, 7, that's my second column. Next we have this theorem. So let A, B denote matrices whose sizes are appropriate for the following. So A transpose transpose is equal to A plus B transpose is equal to A transpose plus B transpose. And then here for any scalars R A transpose equals R times A transpose. And last, AB transpose is equal to B transpose A transpose. For this first property, A transpose transpose equals A, I should put an equal sign here. I'll just look at this example here. We have A transpose is equal to A, B, C, D. So if we take the transpose of this, then each row, so the first row becomes the first column, the second row becomes the second column, and what we have is we get back our original A. This property isn't too surprising, but this one's a little bit different. So let's look at that. So let's look at AB transpose equals B transpose A transpose. And the thing that's different about this is you can't just put the transpose and say AB transpose equals A transpose B transpose. You have to switch the order of A and B. But let's look at an example. So AB transpose, let's say A is equal to 1, 3, 2, 4, and B is equal to 0, 1. I wanted small matrices, small numbers, and then we're going to transpose it. So first we do the matrix multiplication, and we get 2, 4, and then we need to transpose it so we have the rows 2, 4. By this theorem over here, that should equal to B transpose A transpose. So let's take the transpose of A. So here, the 1, 2, the first row, 1, 2 becomes the first column. The second row, 3, 4, becomes the second column. And for B, we're going to transpose 0, 1 into a row 0, 1. And now we're going to take B transpose times A transpose. And then remember, it's not equal to A transpose B transpose. You have to switch the order. So B transpose A, so that's 0, 1 times 1, 2, 3, 4. And what we get is 2, 4. So we've kind of shown this is true for this example. Now we'll look at a couple of examples of applications. So looking at this 2x2 color block examples, first what do we want to do? We want to assign 1 to each block that is blue and 0 to each block that is white. So this is blue, so it gets a 1. This is white, so it gets a 0. White, 0, blue, 1. Next, we're going to place the numbers of vectors by placing the numbers in each column below the numbers in the column to its left. So here we have this 1, 0 column, the green column. We're going to place it in a vector. And then here, we're going to place this column, the 0, 1 column, below the numbers in the column to its left. This is the column to its left, so it's going to go below those numbers in the column to the left. So our vector v is equal to 1, 0, 0, 1. Here's our white color block, so it gets 0, 0, 0, 0. And so our w, which stands for white, is going to be 0, 0, 0, 0. And that, again, is the all-white square pattern. So we're going to let the matrix M equal 1, 0, 0, negative 1, 0, 1, 0, 0, 0, 0, 1, 0, and negative 1, 0, 0, 1. And this matrix, we're going to call it M because it's magic. In other words, no one told us how we got it. It just appeared. So this is the magic matrix here. And what you want to notice is that V transpose M times V, this particular V, is equal to, here we have the transpose of V is 1, 0, 0, 1, right? This column becomes a row. And then we have our matrix M times our vector V. So when you multiply this out, you get the 0 vector. Also, for the white matrix, when you take the transpose of the white matrix, the zeros, times the M, times, oh, this should have been a column, I'll fix that, that also equals 0. So it can be verified that for any other vector x generated from a 2x2 block of white and blue squares, if the vector x is not v or w, then the product of x transpose mx is non-zero. So that means if a computer checks the value of x transpose mx and finds it is non-zero, then the computer knows that the pattern corresponding to x is not this checkerboard here, and it's not the all-white squared. In particular, it knows it's not all white. But let's say it's equal to, well, actually, before we do that, let's do one more example. And this is our other checkerboard. Oh, actually, it's not a checkerboard. It's another 4x4. But here we have blue, blue, so that's 1, 1. And then we have white, blue, that's 0, 1. And that was my phone, not yours. So x transpose mx here is equal to 1. So you can see it's non-zero. And in general, anything that's not this checkerboard or not white is non-zero. But I also calculated, not that it was my idea, but the book said to calculate x transpose x, and that's equal to 3. And if you calculate x transpose x for the checkerboard, that's equal to 2. So now The idea is if you calculate this X transpose MX and it's non-zero, then you know it's not all white and it's not the checkerboard, it's something else. But if you find it's equal to 0, how do you know if it's the white or the checkerboard? Well, the X transpose X is equal to 2, whereas for the white, X transpose X is equal to 0. So that's how you distinguish the checkerboard from the white, is you calculate X transpose X. This next example is an example of scrubbing data to prepare it for processing. So the dates of ground crew accidents for January and February of 2020 are listed in the column matrix T for Toronto Pearson Airport and matrix C for Chicago O'Hare. So here's T and here's Chicago O'Hare, and these are dates. But you'll notice the data is listed differently in the two matrices because Canada and the United States have different traditions of whether the month or day comes first when writing a date. So here, these are apparently days and these are months, right? Because there's no 23rd month, so these must be days. Whereas here, these are the days and these are the months. For matrix C, the month is listed in the first row and the day is listed in the second. Here. Oh, and for matrix T, the day is listed in the first row and the month is listed in the second row. So in order to use this data, the first and second rows need to be swapped. And so notice that matrix A, this matrix A, switches x1 and x2 coordinates of any vector that it is applied to. So A times T gives you this matrix, and so now the data is in the same form, and matrix AT and C can now be fed into the same computer program or same machine. Now we've covered all the main topics of matrix operations. I have a few more problems to do, but since we've covered everything, I'm going to suggest that when you see, you see the problem statement, you pause the videos and give the problem a try before you go and look at the solution. Here, since vectors in Rn may be regarded as n by 1 matrices, the properties of transpose applies to vectors too. So given that A is equal to 1, negative 2, negative 3, 4, and x is equal to 5, 3, we want to compute AX transpose, X transpose A transpose, and X transpose X. And then last is A transpose X transpose defined. Here are my solutions for AX transpose. I have A times X, and then I'm going to transpose it. So I do the matrix multiplication, and I get 1 times 5 plus negative 3 times 3, and then negative 2 times 5 plus 4 times 3, and then I need to take the transpose of that. So here inside I have negative 4, 2. To take the transpose, I'm going to have the row negative 4, 2. To compute this next X transpose A transpose, I'm going to use this property up here at the top of the page that I just circled in blue, which says if you have the product of two matrices and then you take the transpose, that's equal to each matrix transposed, and also the order of the matrices is changed. So that's B transpose, A transpose. So in other words, X transpose A transpose should equal to AX transpose, which we just computed. So this next answer for X transpose A transpose should equal to negative 4, 2. But I went ahead and did the calculation full out just to confirm. So I have X transpose, where is X, which is the column 5, 3 now becomes the row 5, 3, and A transpose. So here, the first row 1, 3 becomes my first column, and the second row, negative 2, 4, becomes my second column. I do the multiplication out, and I get 4, 2. And again, this is X transpose A, and it is in fact equal to AX transpose. The second question was X transpose X. So here I have X transpose 5, 3 times X, and that gives me 34 because that's the 25 plus 9, right? The row times the column, 25 times 9. And finally, honestly, isn't it a giveaway that this is not defined, because otherwise it just would have asked you to compute it. But anyway, A transpose X transpose. So A transpose we have here, we take the first row 1, negative 3, that becomes the first column. The second row, negative 2, 4, that becomes the second column. And then X transpose, which is equal to 5, 3. And then here, this is a 2 by 2. This is a one row, two column, so these don't match. If you try to do the row times column, the 1 times 5, then the 2 has nothing to multiply, so this is not defined. And as I said, that was sort of a giveaway, but anyway, now you know why. The next problem is let A be a 4x4 matrix and let X be a vector in R4. What is the fastest way to compute A squared X? Count the multiplications is your hint. And what a computer science question to ask, but totally valid. So let's see what we can do with that. It helps me to see visually what A looks like. So I just wrote a 4x4 matrix, just putting in the variable A11, A12, A13, A14, etc. for A. And then X, I wrote as X1, X2, X3, X4. And I'm going to consider A squared times X versus A times AX. So when I look at A squared, that's A times A. So according to our matrix definition, that's A times the first column vector of A times the second column vector, A times the third column vector, and A times the fourth column vector. So I want to know how many multiplications each of these A times the column vector equals. So in other words, A times the column A sub I. So I looked at A times the first column vector. So here's A, and my first column vector is A11, A21, A31, A41, this column here. So when I do this multiplication, I'm going to multiply this row times this column. That's 4 multiplications, right? The A11 times A11, A12 times A21, A13 times A31, and A14 times A41. So 4 multiplications. The second row times the column is another 4. The third row times the column is another 4, and the fourth row times another column is another 4. So that's 16 multiplications for A times the first column vector. And you have 4 column vectors. So it's going to be 64 total multiplications just to get the A squared. So now you have A squared. To do A squared times X, well, A squared is again a 4x4 matrix, so it looks something of this form. Your X is, of this form, X1, X2, X3, X4. So it looks a lot like this form here. There's 4, it's a thing in R4. So this A times a vector X is again going to require 16 multiplications. So in total, you have this 64 to get the A squared, and then this additional 16 to get A squared times X. That's 80 total multiplications. Compare that to A times X. So we already said A times X is 16 multiplications. And then A times X, well, this is just a vector now. Is that right? A times X. Yes, it's just a vector. So this is another 16 multiplications. So that's a total of 32 multiplications. So obviously, the second way is the faster way to do it. You wouldn't think it would be such a big difference, but I guess if you're in computer science, 80 versus 16, well, I would definitely prefer to do 16 multiplications by hand than 80 by hand. So definitely this is a big win in my mind. The last problem, suppose A is an M by N matrix, all of whose rows are identical. And suppose B is an N by P matrix, all of whose columns are identical. What can be said about the entries in A, B? You might kind of guess, since you're multiplying rows of A times columns of B, that they're all going to be the same because all the rows are the same, all the columns are the same. So that's really the answer. But I'm just going to show you an example. A is a 2x3. So here I have A11, A12, A13. And since the rows are all identical, the second row, I also put A11, A12, A13. And let B equal be a 3x2. And I wanted small matrices. So anyway, so B, I have B11, B21, and B13. And since all the columns are equal, my second column is equal to the first column, B11, B21, and B31. And here's A times B. And again, since you're multiplying rows times columns to get this first entry, and then for the second entry, you're multiplying this row times this column. And since the columns are equal, these two will be equal. Here you're multiplying row times column, so it's also equal, and last row times column, they're all equal. So all the entries are equal. And so in other words, AB is equal to this scalar here, A11, B11 plus A12, B21, and A13 and B31 times the matrix 1, 1, 1, 1. So to review what we covered in this video, we talked about matrix operations. First, we talked about how to add two matrices. So if A and B are both M by N matrices, they have to be the same size, then A plus B is the M by N matrix whose columns are the sums of the corresponding columns in A and B. Then for scalar, to multiply a scalar times a matrix, so R times A, where R is a scalar, is the matrix whose columns are R times the corresponding columns in A. Then we had this theorem that talked about different properties of matrix addition and scalar multiplication. We had the commutative property, A plus B is equal to B plus A. We have this associative property, A plus B plus C is equal to A plus B plus C. We have this zero matrix, so A plus a zero matrix is A. We have this distributive property of a scalar times matrices, so R times A plus B is equal to RA plus RB. We have R plus S times A is equal to RA plus SA, where R and S are scalars, and R times SA is equal to RS times A. Then we defined matrix multiplication. So if A is M by N and B is N by P, in other words, the number of rows in B has to match the number of columns in A for matrix multiplication to be defined. But when we defined A times B, we can define that as matrix A times the column vectors of B. So this definition of matrix multiplication was nice to give us different insights and also nice for proofs. But we also had a different way of defining matrix multiplication, which was maybe a little more efficient, where if we wanted the entry of AB, which is in the ith row and jth column, that would be the ith row of A times the jth column of B. Then we looked at properties of matrix multiplication. We had the associative law, we had the left and right distributive law, we had this rule for scalars, R times A times B is RA times B, which is equal to A times RB. And then we had this identity matrix for multiplication. We also, just as important, had three properties that matrix multiplication does not follow. One, matrix multiplication is not commutative. In general, AB does not equal to BA. Also, cancellation laws do not hold for matrix multiplication. So if A times B equals A times C, you cannot just cancel A and assume that B is equal to C. And if AB is equal to 0, you cannot conclude that either A is equal to 0 or B is equal to 0. Then we define the powers of a matrix. So A to the K denotes the product of K copies of A. And then we define the transpose of a matrix. So given a matrix A, the transpose of A is the N by N matrix, whose columns are formed from the corresponding rows of A. And then we had some properties of the transpose as well. And that's it for this video. Thank you for watching.